Hello, welcome back to another episode of Math with Haas. You are watching Precalculus, Season 2, Episode 13, Part 3. We're continuing our discussion of trigonometry, and in particular, we are continuing our investigation of the graphs of the 6 trig functions, and in this video, we look at secant and cosecant. So let's go ahead and start with y is equal to secant x, or secant theta. It doesn't really matter what we put as our independent variable here. So for secant x or secant theta, in fact, I'm going to scribble that out and put theta. I'm going to undo that. That looks terrible. Yeah, secant theta. All right. So y is equal to secant theta. We can start by making a table of values. So theta, y, and we can start plugging in values. So to understand what's going on, we gotta remember that secant theta is equal to 1 over cosine theta. So let's start. If I plug in 0, well, cosine of 0 is 1, so 1 over 1, that's 1. If I plug in, how about pi over 4? So cosine of pi over 4, we know is square root 2 over 2, right? So that means secant of pi over 4 is 1 over root 2 over 2, which is 2 over root 2, which we know is going to equal root 2. So this is square root 2. If I plug in a pi over 2, we run into a problem though, because cosine pi over 2 is 0. So 1 divided by 0, undefined. And let's go ahead and go in the negative direction. Negative pi over 4, that's still in quadrant 4, so that means cosine's positive, so we know this will have to be root 2. Or we can just remember our even odd properties from before. Right? Cosine of negative theta is equal to cosine theta. Handy. Now, negative pi over 2 will also end up being undefined. This is already shaping up to be an interesting graph. We know we're going to have vertical asymptotes because at these particular values we're dividing by 0. Now, when I do, let's try, how about 3 pi over 4. Okay, so cosine now is in quadrant 2. So quadrant 2, 3 pi over 4, that is going to be, cosine of 3 pi over 4 is negative square root 2 over 2, so this is going to be negative root 2. And when we do pi, we get negative 1. And similarly, 5 pi over 4, negative root 2. And then notice, if I plug in 3 pi over 2, we get undefined. Alright, so we've identified 3 asymptotes. We got this nice handy table of values, so let's go ahead and start graphing. So, our asymptotes, let's see here, we got one here at pi over 2, so there's pi over 2, and then here's another one at negative pi over 2. And we have a third one here at 3 pi over 2. Alright. Now, when we graph 0, when theta is 0, we're up here at 1. Now, when we are at pi over 4, which is right here, pi over 4, negative pi over 4, we saw that we were at square root 2. Well, square root 2 is about 1.4. That's somewhere up here. Alright. So now the question is going to be, what is happening in between pi over 4 and pi over 2 as theta gets closer to these asymptotes here? So what's happening in between here? So if we think back to unit circle for a moment. You probably knew it was coming at some point. So here's our pi over 4. Here's our pi over 2. Negative pi over 4. And over here we have negative pi over 2. Now, in quadrants 1 and 4, cosine is positive. This means secant is positive in both these quadrants. So when we consider cosine getting closer and closer to pi over 2, it's getting closer and closer to 0, right? Because cosine of 0, or cosine of pi over 2, cosine negative pi over 2 is 0. So that means when we think about the behavior here, so cosine of pi over 2 is equal to 0. So as theta gets closer to pi over 2, secant is approaching 1 divided by 0. I don't like that. How about 1 divided by, really, I don't like that. Alright. We'll just say it this way. Secant theta is acting like 1 divided by really small number. So we know at pi over 2 it's 1 divided by 0. So that's the asymptote. We can't divide by 0. So as we get closer and closer, we're dividing by really small numbers. So like right before 0, like 0.0001. Well, 1 divided by all those 0 1s. So 1 divided by 0.00001, however many zeros I just said, that's going to be some ginormous number. Because if you recall, 1 divided by .001, well, that's 1,000. So every 0 you add in is going to add another digit. So as we get closer and closer to 0, we're going to get bigger and bigger values. So it's acting like 1 divided by a really, really small number. To be more precise, so we'll just box it. So as theta is approaching pi over 2, secant theta is approaching infinity. So this is, might as well take a look. There's some lovely mountains right there from Oregon. Alright, back to this. Alright, so we got, as theta is approaching to pi over 2, secant theta is approaching infinity. This is the precise mathematical language we want to use and precise mathematical notation. So that means this is going up like this. And we can make a similar argument to show that this is also the case here. So it's kind of like a referee putting his arms up for a touchdown. If you're into that sports stuff, that is. No judgment either way, though I do not partake myself. Alright, -1. So, oh, whoops, that's not a point there. Undo. So when we consider our next set of values, I'm going to start with pi, because that's at -1. And we graphed the two values directly in between, right? That 3 pi over 4 and that 5 pi over 4. And that is going to be, well, let's say we should mark that as √2. Right here is -√2. And so that's somewhere right about there. Now, in quadrants 3 and 4, so pi is over here, right? So when we consider going from pi over 2 to pi, cosine's negative, which means that it has to go to negative infinity. Similar from pi to negative pi over 2, or I guess in this case it would be to 3 pi over 2. This here is also going to negative infinity because cosine is negative. And so that means we got a downwards U shape here, which is pretty cool. And now we can make some observations about this graph here. So this was y is equal to secant, undo, theta. And we can see right away that the domain is again restricted. It's going to be all real numbers except where our asymptotes are. So I'm going to just start with pi over 2, and I'm going to consider the integer multiples of it, so in pi. So the distance from negative pi over 2 to pi over 2 is 1 pi, similar from pi over 2 to 3 pi over 2. So if I add integer multiples of pi to just pi over 2, that will give me every single asymptote for all of infinity. So we're going to say all real numbers except pi over 2 plus n pi, where n is a integer. So this funny z here refers to integers. This funny r refers to real numbers. Alright, so funny r, real numbers. Funny z refers to integers. Alright. Range. So what are all the outputs here? So the outputs we got from 1 to infinity and from -1 to infinity. So I'm going to use interval notation. -1 to infinity union with, undo, 1 to infinity. So this says we're including all the values here and all the values here, but we're missing everything in the middle from -1 to 1. Last thing we can note is the period. Now you might think the period is going to be pi, because you think, well, from here to here is one u, and then from here to here is another u. But we have to keep in mind the graph is going to include both of these quote-unquote u's, because this one's going up, this one's going down. If we were to repeat this, we don't really have room on our side, but we'll see on this side it goes down, then it goes up on this side here, and it just alternates. So it is both the 1 u up, 1 u down, that gives you the full period, and that is going to be 2 pi. Because the distance from -pi over 2 to 3 pi over 2 is 2 pi. So that's a good summary there. Let's get rid of this. So right here is our nice summary of secant and cosecant. Oh, I said cosecant, but that is jumping in there. That's my bad. Let's go ahead and look at the Desmos graph, get a nice diagram. Alright. Let's see here. Here is lovely Desmos. So here is secant. Let's see, lovely, used for infinity. Very awkwardly shaped use because they are really thin. And here is our 3 asymptotes that we came to know and love. And we can see that there's infinitely many asymptotes again. Alright. Now, probably what is one of the coolest things about this graph is when we graph secant with cosine. So if we remember, secant is 1 over cosine. So it's not a coincidence that the range here does not include from -1 to 1, because that is directly relevant to cosine's range. Cosine's range is from -1 to 1. And we can see the parallels here. So we can see that every point of intersection here is a integer multiple of pi, and that is when pi, when that's because like cosine 1 and pi, or like pi, 0 pi, 2 pi will give you a value of 1 and -1. And we can see this really cool relationship here where cosine just interweaves and connects all the dots, all the pieces, which is pleasant to look at. Alright, we got business with cosecant now. So, cosecant, you are up. Last but not least, to be cliche about it. So, cosecant theta, we can make a table of values, but as we saw with the cosecant, we don't, or with secant, we only need to think about when does sine equal 0, first of all. So cosecant theta, is, if we recall, is 1 over sine theta. So if we can figure out where sine is 0, then we know where the asymptotes are. So, let's see here. If we think about sine, it's 0 at 0, pi, 2 pi. So sine is equal to 0 at theta equaling 0, pi, comma, 2 pi. In fact, we can say n pi if we wanted, where n was an integer. So that's going to tell us where our asymptotes are, because we can't divide by 0. So now the question is, when does sine equal 1 and negative 1? Because when we think about secant, we had this behavior with the u's where they start, right? This is like the lowest point, this is like the highest point for this u and this u. That gives an idea where are the u's and what if they're going up and down. So if we can identify that, then we know our behavior. So sine theta is going to equal 1 at pi over 2 and negative 1 at 3 pi over 2. And so we'll put this information together. So asymptotes. So there is 0. There is pi. There is 2 pi. Alright, looks like I need to extend this black line out a little bit more. Now, we said that at pi over 2, we were at 1. So there's 1, and this is going to have to go up. And we know it has to go up because sine is positive in quadrants 1 and 2. Quadrants 1 is when theta is from 0 to pi over 2, and quadrant 2 is from pi over 2 to pi. So that's why I know it's going up. We could make some argument we made with secant, but at this point that's kind of repetitive, so I'm just giving you kind of a summary, a way of thinking about it more quickly. Similarly, sine is negative 1 at 3 pi over 2. So here is 3 pi over 2. Here's our negative 1. And for quadrants 3 and 4, sine is negative, right? So that means cosecant has to be negative, and so that means we have to be going down. That's our graph. Took us, what, 2 minutes or something? Cray. Alright, here is our lovely Desmos graph. I had hid it in a folder so you couldn't see what we're going to do. Cosecant. There is our asymptotes. And there is our lovely sine. Pleasant to look at. Exact same behavior. And now we can notice another significant fact. So we've noticed with tangent, cotangent, sine, cosine that they appear to be shifts of each other. Similar situation here with secant and cosecant. So again, it looks like that secant and cosecant are just horizontal shifts of each other, but for now, it's an unproven fact. Alright, so this concludes another episode of Math with Haas. If you have been enjoying our content, please subscribe and consider supporting us on Patreon. Other than that, thank you for your support. Thank you for joining our math party, and I will see you next time.